Let's continue. Our next talk is going to be again by Alexey from Intel about the LLVM SPIR-V backend.
Okay. Thank you. So yeah, I will be talking about SPIR-V backend, and this talk is actually like presented or prepared to you by Vyacheslav. I'm just presenting on his behalf. So yeah, let's talk. It also says like SYCL implementations, but the talk itself will speak a little bit more about other applications of this SPIR-V backend and stuff. We will start with a brief recap. What is SPIR-V? How do we use it? Why do we use it? And then we will move into the main section, which is like what SPIR-V backend looks like today, why it exists, how does it compare with the other existing solutions, what is its state of in terms of like quality and progress that made on it, some technical challenges, and some summary. So SPIR-V, as you probably know, is a binary intermediate language representation suitable for both like graphical shaders and compute kernels. And yeah, it's just a portable binary format to connect things. It is used in many places like OpenCL, SYCL, LLVM, Vulkan. It's kind of like cross-vendor unifying thing. Specification is defined by kernel group, but vendors could bring their own extensions or define client API specifications to like customize how SPIR-V behaves in their specific environment, device, or whatever. And Kronos website has this nice picture which kind of shows you like the place of SPIR-V within the ecosystem. Many things use it or go through it, and I don't know, for example, you could compile your JLSL through some compiler down to SPIR-V and then use another thing to, for example, target metal through Vulkan. So you can connect quite different technologies through SPIR-V. Specifically for computing, which we are interested in as like implementers of SYCL, we also use SPIR-V quite widely. For example, the right picture is our SPIR-V, or I mean SYCL compilation toolchain, and we use SPIR-V as once again universal transport layer because, for example, all our backends like CPU, GPU, even though they're all LLVM based, they still use different LLVM versions, potentially some customizations in their downstream. And SPIR-V is well defined. It has specification. It is stable. So we even like without going to different technologies, we're just using it to unify a single software stack, which is right. And for example, we also use it for AI in our Triton compiler as a possible path to our GPUs. Right now, what we use to work with SPIR-V is a SPIR-V LLVM translator. It is both a tool and a library for bidirectional translation. You can go from LLVM to SPIR-V and back. It is mainly focused on support of compute SPIR-V capability or kernel capabilities, so like OpenCL kernels, targeting level 0 and stuff, and it doesn't really support graphical shaders. So shader capability support is, I think, non-existent basically. It is a robust tool. It has been around for quite a while. It's stable, it's good to use, but there are some problems with it, is that it is not in LLVM upstream. And that makes it harder to integrate it for a new project. If you're LLVM based, you do not get it out of LLVM, you have to get it from somewhere else. You may need to spend extra efforts to keep it in sync with the upstream, and we as maintainers also need to do that. There are some talks about it on some of LLVM developer conferences, and I think it was talk from Kronos, and there were also presented some additional challenges both for end users and for the ecosystem with the translator not being in upstream. There are a few attempts to push it to the upstream. They all kind of failed except for maybe one, where Clang at some point was actually capable of calling to the translator as an external tool. But once again, I believe that the translator itself wasn't shipped with the Clang. So a user who would like to target SPIR-V using Clang frontend would have to get translator from somewhere else separately. So not a great user experience, even like we are halfway there. And through all those attempts, the feedback we received from the LLVM community was like, we have backend code gen infrastructure. Why don't you use it? You should use it. And here we are. Finally, years later, we now have SPIR-V backend in the upstream LLVM. It's an official target, and it provides you code generation down to SPIR-V. So you can grab your favorite, I don't know, LLVM-based front end, your favorite LLVM optimizations, and then pair it with the backend and get yourself a tool chain. It only focuses on one thing, one direction, one path from LLVM IR to SPIR-V. It can generate both text representation for human readable debugging, testing, or binary format. And yeah, it's based on existing code gen infrastructure. It's kind of an alternative to the translator. Why it is a thing? So our ultimate goal of getting first-class SPIR-V support in LLVM is achieved by that. Being in LLVM brings some benefits, like LLVM folks now should be a little bit more responsible with what they do. We also have a little bit more leverage on them being part of the project. We could help, I don't know, shift design LLVM to better suit SPIR-V needs and the ecosystem needs. And yeah, it provides a lot of opportunities for everyone just because it's out-of-the-box solution already. Backend is being maintained by representative of Kronos Group, like, you know, Intel, Microsoft, Google folks are contributing code to that. Unlike the translator, it also supports shader capability. So there's like common core, which get benefits from both works working on shaders and compute. So it's somewhat like easier to develop or moves quicker because more code reuse and stuff. And the team, of course, closely collaborates with different Kronos working groups to make sure that all the needs are fulfilled and the backend moves in the right direction. And it already has uses some uses outside of like Kronos. For example, Microsoft announced that DirectX will use SPIR-V at some point in the future. And yeah, just presence of SPIR-V there makes it easier for anyone to target it and therefore enabled it in their toolchain, or for example, enables their accelerator through SPIR-V. It's now easier, or their language through SPIR-V. Let's compare it with the translator. And as of now, backend is good and stable enough for us to pass both SYCL conformance suite and OpenCL conformance suite with it using our Intel implementations of those. It allows you to specify target SPIR-V version, I think from 1.0 to 1.6, enable or disable extensions, which we would like to use. And the main difference with the translator is that it does not support all the extensions we have in the translator, but if you don't care about them, then you're perfectly fine. Some specific examples are on the slide. They are somewhat like SYCL-centric, simply because, like, from our point of view, that is what we are missing to get all the features through the backend. But yeah, it's in a pretty good shape overall still. For the past year and a half, a serious uplift was done to the backend, multiple internal refactorings, like lots of new SPIR-V extensions were added. We ramped up support for optimized LLVM IR. The problem with optimizations is that you get new patterns, you get a lot of more intrinsics, which you haven't seen earlier, and now you need to deal with them. And right now, the backend is also capable of dealing with optimized IR. Some bugs in the translator as well were found along the way, like some patterns the translator haven't seen and couldn't reverse translate, they were fixed. And yeah, in general, like good contact with overall LLVM community was established along the way. In terms of quality, there is a dedicated testing suite, like 600 plus tests today, and it's growing. Some bigger test suites are being embedded. The test suite covers like different aspects of the SPIR-V, different subcomponents, or I don't know, different subcomponents of the backend as well. And SPIR-V web validator is also being used in it. So we know that SPIR-V we produce is actually valid in context of the specification, and it's all automated using GitHub Actions, per commit, etc. Some external testing exists as well. For example, at LLVM, we have a regular run of our SYCL tests through SPIR-V backend, I believe even in pre-commit, not also in nightly. Our XPU backend for Triton has some CI workflows which go through backend and test it. Sometimes it is hard to keep that testing, I don't know, absolutely 100% because lots of moving pieces, like, I don't know, driver changes, our SYCL implementation changes, LLVM changes, and considering that all those projects with external integrations are downstream, there is some time lag when we integrate the latest fixes, updates, or everything into backend. Some non-functional testing has been performed. For example, a little bit of compile time performance of the backend itself. For the past a year or so, the backend was sped up significantly, like 25x. It is, strictly speaking, technically still slower than the translator, but from what we have seen, it is good enough in our toolchain, so it is not a bottleneck there. We have previously seen there are other bottlenecks in SYCL compilation. Some very, very preliminary testing was done to assess the performance of the generated SPIR-V. So what do we generate? Is it make sense or not? We just took a single benchmark on some PVC GPU, and it seems like on pair we haven't found any drastic difference or anything. It was within a margin of error. But once again, it was very preliminary testing, very like small scope, and more work should be done on that. And some more integrations, as far as I'm aware, are being done. Like we have some Intel extensions for OpenCL projects, and SPIR-V backend is being evaluated and attempted to being used there. Some our ML layer-based compilers, and yeah, we are ramping up our SYCL tests as well to use backend more in there. With respect to community, we have a team of dedicated contributors. There are like regular working group meetings within LLVM, which you can join. There is a LLVM calendar, so you can go there and participate in backend development, see what's going on, ask questions or whatever. It is being pretty regularly covered on conferences like today and literally next week, Vyacheslav is going to LLVM Dev to talk about SPIR-V backend progress there and talk with folks about it. And it has good documentation, like there is one for end users, like how do you even use it in Clang, and there is one more detailed, like which extensions are supported, how do you enable, disable them and everything. So yeah, documentation is good, I think. There were some challenges to implement SPIR-V backend, and fundamentally they're caused by the fact that what LLVM Code Gen expects to be a target is way lower level than SPIR-V is. SPIR-V is a relatively higher level language, somewhat close to LLVM-IR, and LLVM Code Gen expects something more low level. And there is just fundamental difference which we had to overcome to make it all work. So yeah, some definitions or expectations from a target representation which are in global ICER or machine verifiers that just difference that do not apply to SPIR-V. A few examples here, like for example, backend generates constructs like if condition then statement, and that's it. But in SPIR-V with op-branch conditional, you can only do full if then else. And therefore you need to do some tweaking to generate slightly different thing. Labels have slightly different semantics. There are some issues with aggregates, like in SPIR-V you can represent high-level data types like structs and everything, but in assembly language, they're not exactly expected. So some tricks had to be done to kind of still preserve them and I don't know, make backend aware that it exists. Our SPIR-V is not as low level as you would expect it to be. And of course, a pack pointer. LLVM moved to pack pointers a while ago, but SPIR-V spec, all pointers are typed. So it's quite a challenge to like re-inference all those pointer types. And it's important for consumers as well. In some cases, they're very sensitive to like pointer type changes or whatever, because once again, patterns are different and I don't know, some things may depend on them quite heavily. In summary, as of now, since January this year, backend is not in experimental state anymore. So it is built by default. And I guess with the next Clang release, I'm not sure if it made a cut or not. You will be just able to, I don't know, write a code, pass an extra option, and get SPIR-V out of Clang right away out of the box from, I don't know, just an auto release. Functionally and performance-wise, it isn't drastically different from what we have right now with the SPIR-V translator, so it is pretty much suitable for adoption already. Of course, there are gaps, things to improve, but the more feedback we have, the quicker it will ramp up. And we could even say that right now it grows faster than the SPIR-V translator because more folks are interested in the backend. We see benefit of supporting both shader and compute because common part grows quicker because it's shared between the two. And yeah, presence of like this backend in the upstream, it makes a lot of things easier. And in general, I don't know, I guess Ardent's position in the industry, in the ecosystem, makes it more visible, makes it, I don't know, more reliable and everything, and in general promotes it to other folks outside of, I don't know, heterogeneous computing or whatever. So yeah, try it yourself. I'll let folks know there are multiple links to like working group and everything, and I guess their backtracker is just general LLVM backtracker. So whatever we find reported there, and the team will pick it up and work on it. And some next steps here, like what are the plans going forward for the backend? Of course, continue to enhance it, add more features, add missing extensions, incorporate whatever feedback new users have, gather more users, work more on improving quality of testing, like we talked at. Performance testing haven't been done that much yet. Compile time testing could also be improved and stuff. And we actually have plans to release one API that parallels C++ compiler with SPIR-V backend enabled by default somewhere next year. We'll see how it goes. We'll see when we reach this goal, but that's the plan. Of course, it will be possible to like switch back if you see any issues or if that's necessary, but we would like to officially use it in our own production. And yeah, that's it. That was crypto.
So it may be a minor question, but you have mentioned that with LLVM backend CTS conformance test is already passing, correct?
Yeah, it could be like 99% passing. I don't know I haven't been provided with the exact pass rate, but it's like practically we are there.
Yeah, now I'll take a question. On which device?
Good question, but I will need to ask Vyacheslav about it. I assume it was GPU.
Okay.
Intel GPU, I mean.
Intel GPU.
Yeah. Okay. Okay.
Okay, thank you.
I mean, the backend in upstream LLVM only solves half the problem in the sense that you can now go from LLVM IR to SPIR-V in upstream LLVM. Is there any plans to add the other direction, like a front end or importer tool to go from SPIR-V to LLVM IR in upstream LLVM?
Okay, yeah, I talked about that with Vyacheslav, and from what we see right now, there is not demand, but there is no interest of having like reverse translation in the upstream LLVM IR as of now, from what I understand. Maybe the reason for that is because, I don't know, reverse translation is more about consumers, and every consumer kind of have their unique needs. Maybe they're based on different LLVM version or whatever, some customizations, they need something different. So it would essentially require us to unify reverse representation of SPIR-V in LLVM IR, produce some common standard. And as of now, I don't think that there are lots of interesting parties, considering that this is already more or less deep into backends and everyone does their slightly different or their own thing. So as of now, no, we plan to continue to support and probably use SPIR-V LLVM translator as just a component of our backend implementations to keep reverse translation in place. So yeah.
Thank you.
Mentioned that opaque pointers was a pain point for you, as probably for many in the LLVM community. So my question is there anything that you're trying, any change that you're trying to push for, or what would you like to wish from the LLVM community?
Unfortunately, me personally haven't been involved in that effort like at all. Right. So I unfortunately don't know the details. I know that some of our folks actually pushed something into LLVM, some metadata or something, or some, I don't know, maybe it was like target information for pointers, which kind of allows to still preserve some information which is necessary for SPIR-V. So I know that something was actually done to LLVM to make our life easier, but unfortunately I don't know the details and can give any like my wish list because I'm not the one who is working on that.
Yeah, brief follow-up to your question. The SPIR-V working group is, there's a provisional extension that you can see. It's in public, that does untyped pointers in SPIR-V, which should hopefully make this easier on the SPIR-V producers once the SPIR-V consumers support it. So maybe the call to action is to nag your favorite SPIR-V consumers, make sure that they support the extension. I do want to call out one other thing. I know this was a presentation largely about SYCL, but the SPIR-V backend is getting contributions from lots of other folks outside of this room on the graphics side, which is really cool to see. And I think there's even been some usage of the SPIR-V backend from AMD as part of their tool chain. So it's kind of neat to see. Once the SPIR-V backend is in place, there's a lot more people that are using it.
As we seems to have some time, I have a more broad question, which is also related to this topic. As we see upstream effort seems to be going well, is it a sign that we have upstream the translator that eventually the entire D++ compiler would be upstreamed?
It definitely makes it easier because now we have SPIR-V part integrated, but otherwise it doesn't help that much because the whole like SYCL runtime and especially SYCL compiler, it's like completely different story with their own unique problems. So like overall, it's one component less to care about, but doesn't make, I don't know, our work less, simpler, or doesn't significantly change the amount of work we need to do. So we still have plans to upstream that, but it doesn't speed it up like significantly. It's more or less no hope for it.
So at least there is the idea of translation, upstreaming, right? And
the idea of upstreaming was there from the beginning. Resources and priorities were not always there, but our folks are actually actively working on that right now. We are pushing some patches to both like front end and middle end and tooling. Yeah, it's in progress, slowly but in progress.
Okay, thank you.
Mentioned that as you are enabling optimizations, you're starting to hit more LLVM intrinsics and stuff that you need to realize you need to implement. I also noticed when targeting this SPIR-V translator, there are some things that it doesn't implement yet, like the LLVM freeze instruction. So then you need to kind of work around and hack around here. Like, does the backend handle these things in a better way now? How does it compare?
I honestly don't know. I assume that the testing which was done was for like SYCL applications. Mm-hmm. So from that context, it should probably be on pair with the translator because like similar things happen. Yeah. But I guess they had to do like somewhat similar things because unless you have a SPIR-V extension, you can only do so much.
Then let's thank the speaker also for the additional time.